Okay, so in early April 2023, the celebrity scientist slash vlogger Sabine Hossenfelder uploaded a video making the claim that she believes that faster-than-light travel is actually possible, and further expressing the belief that it wouldn't necessarily lead to backwards time travel. I was pretty quick, within a few minutes actually, to post 2 comments on that video, telling her that no, actually, it does directly lead to backwards time travel, and here's why, and I gave a brief explanation, and unfortunately, in the infinite wisdom of the ultra-progressive, Puritan, pro-censorship nitwits that are in charge of YouTube, like much of Silicon Valley, my comment was hidden from all other viewers. So I made a video quickly, and it was a quick and dirty video, and it was heavily downvoted by my minimal subscriber base and possibly fan base of Sabine Hossenfelder that found my video. And it may just be that my subscriber base has no interest in physics. They subscribed because of my tinnitus tentative treatment video, which didn't help me, or they subscribed because of my cat videos. Suddenly my subscribers decreased by 3, which doesn't sound like much, but I only had like 390. So it had 1 upvote and a whole bunch of downvotes, and it could just be that, you know, the fan base of Sabine Hossenfelder that saw my video were enraged and said, "How dare you criticize our goddess?" Or maybe it was just that no one cared. But it also had a small problem with it, which is that I just used the relativistic velocity addition rule as if it was valid where one speed is superluminal, and even ChatGPT, after talking to it, or communicating with it, expressed that it thinks, and it's wrong, it thinks that that formula is not valid if one of the speeds is faster than light. And I will be demonstrating now that it in fact is valid, even if one of the speeds is faster than light. It doesn't work if both speeds are faster than light, because there's no valid reference frame then. In special relativity, you have to have a valid observer. But the way the relativistic velocity addition rule can be derived just as a ratio of the difference in space between 2 events in space-time divided by the difference in time between those 2 events. And that doesn't actually require an actual physical object, that is a reference frame, connecting the 2 events. It's just a ratio of 2 numbers. And every observer will have an observed time coordinate of those 2 events, and every observer in space-time will have an observed space coordinate of those 2 events, and can calculate a ratio of the 2. Now, if the 2 events are far enough apart that they are connected by what is known as a space-like world line, so if they're 10 light years away and they happen 1 year apart, there will be disagreement over which event happened first. So there will be disagreement over which direction an object traveling faster than light connecting the 2 events is traveling. And that is the key to it being useful for backwards time travel. So I have this thing prepared. Here's the scenario. So I have a friend named Bob. He leaves Earth at time 0 at speed v1 in the direction of star X, which explodes after 1 year. So 1 year later, it explodes. It's d light years away, so I don't see it explode until time d plus 1. I'm trying to talk fast because there's a 15-minute time limit on my screen recorder. Anyway, so after d plus 1 years, I see it explode, and at that point in time, I therefore conclude, I can reconstruct when it actually exploded in my reference frame of 1 year. This sort of thing happens all the time in special relativity, where you have to worry about the light travel time. It can screw things up if you're not careful. Bob, however, sees something different. He sees the time and space coordinates transformed by what's known as the Lorentz transformation, which is the original image I had up here. Now, t prime is the time that he observes any event happening at, and x prime is the time that he observes any where it occurs in space. This is a particularly convenient formulation of it for me because I'm only dealing with 1 space coordinate. We're not talking about moving around in 3 dimensions. So this formula is exactly what we want. Y and z are irrelevant. We're just traveling in the x direction, and we're just worrying about how much time has passed. So, if you take this formula, you see how my observed times get transformed to what time Bob observes things to happen at. And so we both obviously agree about event 1. Event 1 is Bob's departure from me. We both think it happens at time 0, and it's space coordinate 0. Now, the other event, the explosion of star X. In my reference frame, I see it explode after d plus 1 years, but I reconstruct when it happened at time 1 year, and I see its distance from me as being d light years. So this sort of pseudo-velocity, the ratio of distance over time between the two events, is d. Now we could choose d, the distance, to be such that it's faster than light or slower than light, but I'm just using it as a variable so that I can show that it doesn't actually matter. Bob, however, the time he observes the event 2, the explosion of star X, is happening, is this complicated thing, and the space coordinate is this complicated thing. So this pseudo velocity, it's not an actual physical object moving. It's just two events in space-time, separated by distance, separated by time. What is the ratio of the distance over time? So if we were to observe a faster-than-light object move from one event to the other, since we both would agree that it left from one event and arrived at the other event when we eventually see it, that expression would definitely describe what we observe that superluminous object's speed to be. And if you take the one thing over the other, this should be 1, not a q. It's square root of 1 minus v squared over c squared. You have d minus v1. You see this thing, the Lorentz contraction factor, square root of 1 minus v squared over c squared, is in both the numerator and the denominator, so it cancels out, and you're just left with d minus v1 in the numerator and 1 minus v1 times d divided by c squared. Now, pulling away the curtain, I now say, well, let's just define velocity v2, potentially superluminal velocity v2, to be d. So, in my perspective, I observe this hypothetical faster-than-light moving object as moving at speed v2, which is not constrained to be below or above the speed of light, and this is the speed that Bob observed it moving at. And this is the relativistic velocity addition rule. And so it does not actually depend on it being a valid reference frame. Now, in relativity, you need to have an observer, and there needs to be a valid reference frame for the observer. So the observers are me and Bob, and we're moving slower than the speed of light, and those are valid reference frames. If you try to have a faster-than-light speed, that's not a valid reference frame. But, you know, and you end up with all sorts of stupid things happening, like you get imaginary numbers for what the Lorentz contraction factor is and what the time dilation factor is. So if someone moved at 10 times the speed of light, according to special relativity, they would experience a passage of time, a proper time of something like I. What does that mean? They're experiencing imaginary time. So you end up with results that don't really make any sense in special relativity. But maybe with general relativity, with your Alcubierre type drive, you end up with a time experienced by the traveler that makes sense. But the fact is that outside observers observing this thing moving faster than light will see what they see. And this is how fast I see it moving, and this is how fast Bob sees it moving. Now, thing to notice about this formula, if you chase after something, let's say d is 10 times the speed of light. If Bob chases after it at 1/20th of the speed of light, you might naively think Bob will see it moving at 9.95 times the speed of light, because that's your everyday experience, where this denominator here is pretty close to 1. But in fact, that's not what happens when special relativity is in play. You might think that a 20th of the speed of light, 0.05 c, is negligible next to 10 times the speed of light, except that it transforms the way space and time work in a significant way. And what do you get in this fraction? You get 10 minus 0.05, so 9.95 in the numerator, but what's the denominator? Well, v1 times v2 over c squared, if v2 is 10 times the speed of light, and v1 is 1/20th of the speed of light, v1 times v2 over c squared is 0.05. 1 minus 0.05 is 0.05, so you got 0.5 is 1 minus 0.5 is 0.5. So 0.5 in the denominator, you're dividing by 0.5, you're multiplying by 2. So the speed that Bob sees this superluminal object moving at, in my perspective, 10 times the speed of light, he sees it not moving at 9.95, but 19.9 times the speed of light. By chasing after it, it only moves faster away from him. He does a worse job of keeping up with it the faster he chases after it. And this is the funny thing that happens with superluminal speeds in special relativity. Now, what does this mean when he reaches 1/10 of the speed of light and this denominator becomes 0? Well, now that means that it's traveling instantly from his perspective. And if he chases after it at 1/5 of the speed of light, at 0.2 times the speed of light, now v1 times v2 over c squared is 2. So it's 1 minus 2 in the denominator. You have negative 1 in the denominator. So now, instead of 10 minus 0.2, you have 9.8 in the numerator and negative 1 in the denominator. You have a speed of negative 9.8 times the speed of light. What does that mean? It means that in Bob's reference frame, it's going back in time. It's going the other direction. Now, he doesn't see it going the other direction because of the light travel time. So if it's fleeing away from him and it gets to 10 light years away after negative 1 year, he'll see it 9 years later. But when he sees it 9 years later, he'll just reconstruct what its actual speed was as negative 10 times the speed of light, or negative 9.8. But he'll still see it traveling in the same direction because of the light travel time. It'll take him 9 years for him to see it being 10 light years away through his telescope as it flees away from him. So, what does this mean for backwards time travel? What this means is that you can accomplish, you've probably heard some nitwit explain to you that, if you went faster than light, you'd be going back in time, and you probably, this probably set off bullshit alarms in your head, saying, that doesn't make any sense. If you travel 10 light years in 1 year, it'd still take you 1 year. You're not going back in time. So if you leave in 2020, you get there in 2021, you get back to Earth and it's 2022. You haven't gone back in time. But here's the trick. You do it from a non-zero starting speed, particularly in the opposite direction. So, if you had a 10c, 10 times the speed of light, faster than light warp drive, how would you use this to go back in time? The answer is, you start from a starting speed of, let's say, 1/5 of the speed of light, faster than 1/10 of the speed of light at least, so that this denominator is a negative number. You start from a non-zero sublight speed, the impulse drive if you're a Star Trek nerd, in the opposite direction. And you head towards this star that's 10 light years away. And at a speed of negative 9.8 times the speed of light, you leave in 2020 and you get there in 2019. You look back at Earth through your telescope and you see it being the year 2009 because it's 10 light years away. Someone watching you on Earth sees you get there after 9 years. And then when you turn off your warp drive, you're now moving away from, in the direction of Earth at a speed of 0.2 c. You grind to a halt and you accelerate the other direction, so you're moving away from Earth at 0.2 c. And you once again engage your warp drive in the direction of Earth, and when you get to Earth, it's now 2018. You've gone back in time 2 years. Now, what this means is that if there was a faster-than-light capable civilization anywhere in the universe, They would have colonized the universe if they were expansionistic. They would be here. They would have colonized Earth billions of years ago. We would see time travelers from the future. That is why the Fermi paradox shows that faster than light travel is probably not possible.